This is the lesson on triangles. The first kind of figure, though, that we want to talk about is a octagon, and this is the bay window on the back side of our house. And if you notice, it's part of an octagon because this front part window right here, and then on each side is a matching window, so that's three sides, and then the left side and the right side are 4, 5, and then you can imagine three more on the backs to make 8. Well, if you look at those angles, you can see that this angle here, here's the right angle to the house, and then this angle here, this measurement is not the same as this measurement of the angle next to it. And in fact, when they put in the soffit, they certainly didn't match that up, did they? They should have had the line drawn straight here. I'll show you the line that I mean, and then you can see, oops, you can see how they should have drawn it instead. The line should have gone from the corner up there. Oops, I didn't even draw that one straight. I'll do it again. Straight down to the corner. Well, I guess I'm not very good at drawing straight lines either. But you can see how that was supposed to have worked there. Next, here is a regular octagon, and you can tell it more easily. One side straight towards us and so on. You can tell it more easily by looking at the cupola up on top. You've got the left side and the right side, and then there's three sides pointing straight towards us. So that's a regular octagon. This is another regular octagon, and if you look at it from underneath, you can see the octagon-shaped key piece right in the middle to which all 8 of the rafters are connected, which helps zoom in on the regularity. Interestingly enough, is the floor drain of that gazebo is right underneath the top, and you can see that also is a regular octagon. There is a scale on your carpenter's square that helps you draw regular octagons, and you can see it here. It starts 0, 5, 10, 15, 20, 25, 30, and so on. I've blown up a section of it, and you can see how the sizes are related. The 5 is a little bit over an inch, about an inch and a 1/16. If you look at how to use that scale, well, we've got a 5-inch square of paper here that I made, and then I found the middle of it, and I put the midpoint at the 5, backtrack to the 0 here. So this 5-inch square, I made a mark at this spot here, and I made a mark at 10. So this distance from the 0 to the 10 would be the same all the way around. This would be that same 10, this would be that same 10, and so on, all the way around the octagon. This is a regular hexagon, and you can see, you can see the 6 sides of the hex bolts, or hex nuts as we say. Interestingly enough, a fire plug doesn't have a hexagonal head, it actually has a pentagonal head. And the reason for that is that you don't have kids on the street opening those valves and turning on the water, because you need a special wrench to open those. Here's another pentagon. This one is in Washington, D.C., and it's a very efficiently shaped office building. There's some kind of rule that they made in 1941 when they constructed that pentagon, that they wanted people to get from one section of the building to the farthest section of the building as quickly as possible, and you can see how these cross hallways made that possible, and everybody got a window. Every room has a window either on the left side or the right side of the building. The other thing that's true is that in the background here we can see the Washington Monument, and here's the Jefferson Memorial. Back here is the White House in this spot here. Here's the Jefferson Memorial. Here's the Lincoln Memorial. And then over on the far out here on this end of the mall would be the Capitol building. This is the angle that the rafter takes to the isosceles triangle of the rafter takes, and if you notice, it's a 63-degree angle. The top angle is not quite 60 degrees. It's actually looks like about 53-degree angle. So this angle up here is 53 degrees, and these two angles down here at the bottom are each 63, which makes these isosceles triangles. I thought this was an isosceles triangle until I measured it, and in fact, no matter how you cut it, it is a scalene triangle. Well, that's assuming this wall right here, or this road right here, was not curved. Here's another triangle, and this is actually an obtuse triangle because this angle up here is obtuse. So I'm sorry, this triangle here probably is an acute triangle because each of the three angles are acute. Here's the measure of that top angle that we saw on the page before. This inside angle up here is, what did it say, 43 degrees. Here's a right triangle. This road here and this road here are at right angles, so we could figure out the area of that triangle quite easily. This triangular shaped lot actually is a real triangle, assuming this side were straight. It's 106 feet along this part here and 106 feet along this part here to the curve. So I thought that was kind of interesting. Finally, if you, well, I'm going to flip this over so that you can see, here's the ceiling of my garage, and then here is another obtuse triangle that it makes up the rafters of my garage. Here's two right triangles across from each other. And here is the last remaining part of my roof trusses. So I'm going to show you like I said, the angle there is 44 degrees. Here's another pair of right triangles across from each other, and they are not isosceles right triangles because this distance here and this distance here are not the same length. The angle, as I said, to my rafter was 57 degrees, and the other angle was 31 degrees, and the other angle was 42 degrees, and 117 degrees. So on my truss here, you can fill in all of those rafter that I'd like you to just put in the measurements that we've been showing you along the way. Surveyors make measurements and then calculate positions based on those measurements. For example, they know the length from this town here, to this spot right here. They know those two positions, and then they measure those three angles, and by doing that, they can calculate out to this position. They can calculate to each of these positions just using triangle measurements. Here's another right triangle, and if you notice right here is the right angle. This is a scalene right angle, and I'd like you to measure these angles, and then as you do, see what size the triangles are. In fact, this angle over on this side should equal this angle on this side, and you see if that's going to be true for your measurements. This is probably a better spot because if you notice, each of the different sidewalks meets at a right angle. I'm sorry, at the angle. So do just the sidewalks here, and you can see that these angles are equal. But more importantly, you can see that if you take this angle right here, in other words, the angle that is opposite those two angles, those two right here, extend this line out, extend those two lines out, you will see how the exterior angles here are equal to the sum of the two remote interior angles. I'd like to show you an example of a similar triangle here with my rafters. What I did is I measured so that this distance from this white ruler up to the rafter is equal, and then I measured along the lengths of the two sides. Here's 6 inches and down here is 12 inches, so that was a 6/12 pitch. I also expanded it to make this 12 inches, this 24 inches, and so it's another 6/12 pitch, but it just shows the whole wall and how this ruler is parallel with my roof rafter. In fact, if you do the math and compare them, you'll notice that it was 99 inches to the roof of my garage, and it's 200 inches, well, 203/8 to the middle of the garage, which I thought kind of interesting, that those are all congruent or similar triangles. Here's another set of similar triangles. Each of these, here's the biggest one, down to the smallest triangles here on this octagonal shaped building, are all similar. Another set of similar triangles, this very small one, each of them gets progressively bigger. Now if you notice, these last two have a part missing. You could take this piece and stick it in right here, but there is no matching piece for this spot that's missing up here. But each of these would be a similar triangle. Here's some more similar triangles, because these uprights on my roof trusses each are parallel, and as you go farther down, the similar triangles keep getting smaller and smaller and smaller. Just I show the hip section of the roof, which we have some work that we can do later on with rafter trusses, and I can show you the math of that. These two triangles they are similar, but they're also congruent, because this length of the blue hypotenuse is the exact same as the length of this brown hypotenuse. Here's some more congruent triangles. If you notice, it's 9 1/4 on that part of the steps, and then looks like about 7 1/4 going up. Here's another step, 9 inches up to 7 1/4. Now they aren't all exactly that distance, because if you notice, this one's 9 1/4, but it's almost 9 3/8, or 7 3/8, excuse me. This one is 7 1/4, but look at that, it's close to 9 1/2 inches. So you can see there's a little bit of tolerance that you can have in steps and still have people to be able to walk up them without tripping. This is 9 inches and 7 1/4. It's much more important to get the height right than the width. Here's 7 inches, so you see that one's not quite tall enough, but look at it, it's almost 10 inches wide. So that step is really not very well constructed, at least within a certain amount of tolerance. Here's another example. I'd like to show you that this distance on the here's 10 inches, so it looks like 11 1/4 inches is the run of the steps, or the tread, and then the riser looks to be about 7 1/4 again. Here's another step. If you notice, it's about 7 1/4. You can't really tell the length of the run. I didn't take a real good picture there. Here's another stair. What is that? 11 1/4 and 7 1/4. So at least they're getting consistent on the height. 7 1/4. Oops, I'm going the wrong direction. Here's 7, and what is that distance? 11 1/2, a little bit over a half. This last one is 7, and I don't know, can we see the length here? Almost, what is that? 11 3/4. So you can see there's a lot of tolerances there. Here's another picture that shows how surveyors work. And if you notice, everything is with triangles. Here we've got some vertical angles. Here we've got some isosceles triangles. Here's a obtuse triangle. So they always work with triangles. The thing that I'd like to show you here is two triangles. I'm going to take a snapshot here so that you can see what I'm talking about here. This triangle that connects the centers of these three irrigation circles, since this distance here is the same as this distance, is the same as this distance, each of those distances are the same. That makes this an equilateral and also equal angular triangle. So each of these is 60 degrees. Now, what we can do is we can take that equal angular triangle and cut it in half so that this is 90 degrees down here, which would make this 30 degrees up here, and then we have a 30, 60, 90 triangle. And if you notice, if this is 1, this section here is 2, and using the Pythagorean theorem, this section would be the square root of 3. The other kind of triangle that you can see from a picture of irrigation circles, I'll show you here, is let's connect these centers. So if you notice, from here to here and from here to here, those are equal. Well, if you add them up, if this distance here is a total of 1 diameter and this distance is a total of 1 diameter, then this is the root of 2 diameter. And if you measured the angles of these triangles, this is 90 degrees. Since these two angles have to be equal, and we have 180 degrees in a triangle, subtract 90, we have 90 degrees left. If we divide that by 2, each of these angles must be 45 degrees. So this is a 45, 45, 90 triangle. Now, another place that comes in handy is if you're making cross braces. If in this picture here, you can see that this cross brace, well, here's a 45 degree angle here. Here's a 45 degree angle here. So if the total length is 18 1/4, we can take that 18 1/4 and I'm going to make this smaller so that I can see the whole thing. Okay, so that's the hypotenuse. If we take the square root of that, 18 and oops. Yeah, I'm going to put the fraction in there. 18 1/4. Let's do it again. 18 1/4 and divide that by the root of 2. We find that each of the sides of that triangle is about 13 inches, the 12.9 inches, 12.9. We can figure out exactly what that is on our calculator. Take that and subtract 12, and so we get that answer, about 0.90. Multiply that by 16. That'll give us how many 16ths of an inch it is. So it looks like 14 16ths. So that's 12 14 16ths, which is the same as 12 7/8 inches. Each of these is 12 7/8 inches. And that's all because this is a 45 degree angle. So you can see how the geometry of triangles really comes into play in our work. One of the things that we're going to discover, or we're going to use in our mathematics, is Heron's or Hero's theorem. What you do in Hero's theorem is measure the lengths of these sides and call them A, B, and C. If you add them up and divide them by 2, you get what's called the semi-perimeter, or half the perimeter. So if you take the square root of the semi-perimeter, subtract each of the sides, you will get, and take that square root, you will get the area of that figure. And if you notice, they calculated the area here as being 1,640, oops, that's the perimeter, 1,644 yards is the perimeter, 122,000 square yards is the area of that triangle here that takes into account these 3 different sized circles. Here's another one. I'm going to show you how these work together. So let's take our picture here of this triangle. And this first distance is 228 feet. Okay? If we take the altitude of that triangle, which is 110 feet, oops, 110 feet, where's our picture? So the altitude was 110 feet, and we calculate that area. Area is 1/2 times the base, which is 228 feet, times the height, 110 feet, and we get an area of 12,540 feet. And when we actually did it, so 12,500 feet. Here's another one. Let's look at this one. This triangle has 186 feet is the length, and the height is 134 feet. So if we calculate that area, we get 1/2 times the base, which we just said was 186. Oops. Times the height, which we said is 134, we get 12,460 square feet, which is remarkably similar to that other triangle that we had before. Those two triangles are almost the exact same area. 12,434 is what they calculated it as. Let's see, what did we say? 12,434. We calculated it as 12,462. So we had slightly different measurements than they did, but that's through rounding that we got those differences. Here's the picture that you're going to need for your trusses that we were talking about before, that you're going to need the different angles, and then the measurements. You can see there's 5 feet and 4 feet, and the distance along the bottom we said was almost 200 inches, and the height was almost 100 inches. So that's the geometry of triangles.